Hello friends, here are some tips to predict the geometry of some molecules and ions. As we know, the geometry of the molecule is the same whatever theory we are going to follow. Now today is a holistic picture as to how we can predict the geometry of a molecule based on octet rule, valence electron pair repulsion theory and hybridization. It all amounts to the same. For this, we have a few tips. A few simple mathematical formula will help you to predict the geometry of the molecule. So the first one is to identify the number of electrons in a molecule. That we can find by the group number and the atoms number in the molecule. You have to sum up the group number into the number of atoms. The next one is to find the lone electrons. That is by group number minus the surrounding atoms multiplied by the valency. And for hybridization, you will take the number of lone pairs plus the surrounding atoms. It may look complicated, but as you do it, it looks very simple. Now the term group number means the groups where the elements are present in the periodic table. Now we are going to see a few structures which have these atoms only. So lithium belongs to the first group, beryllium second group, boron third group, carbon fourth group, nitrogen 5, oxygen 6, fluorine 7 and neon 8. This is the group number and the valency for the first three it is the same. For the remaining it is 8 minus the group number. Now we are going to apply these formulae and get the geometry of the molecule. So let us see a few examples. The first one is carbon dioxide. So to find the number of electrons in the molecule, as I said, the formula is summation group number into atoms. Group number, what is the group number for carbon? Group number is 4. Let us start with the structure of carbon dioxide. Carbon group number is 4 plus 2 oxygen atoms. The group number of oxygen is 6, so that amounts to 16. Here the number of electrons in the molecule should be even number. Only then the molecule can be shown as a structure. So when you write the structure of carbon dioxide, write first the atoms present and connect them with a bond. A bond represents 2 electrons. So there should be totally 16 electrons. 2, 4 are given. So you have to accommodate the remaining electrons in these atoms. So 2, 4, 6, 2, 4, 6, 12, 14, 16. So here the 16 electrons have been accommodated. But if you see carbon, there are only 4. Each atom should achieve the octet according to the octet rule. So these 2 oxygen atoms just transfer their electrons and make the carbon achieve the octet. To calculate the lone number of electrons in the atom, it is group number minus the surrounding atoms into valency. So valency of oxygen is 2. So there are no lone electrons in carbon dioxide. For hybridization, this formula is lone pair. The electron should be lone pair plus the surrounding atom. So 0 plus 2 is 2. 2 stands for sp hybridization. Similarly, you can see for beryllium chloride. You apply this formula. So 2 plus 2 into 7, it amounts to 16. The 2 atoms are bonded. For chlorine, so 2 plus 2, 4. But there are totally 16 electrons. So you have to accommodate the remaining 2, 4, 6, 8, 10, 12, 14, 16. So to find the lone electrons, group number of the central atom minus the surrounding atoms into valency. So there are no lone electrons. So hybridization is 0 plus 2, 2, which is once again sp hybridization. Same way we can calculate for the other atoms also. Let us take the example of boron trichloride. The central atom is boron. It belongs to group number 3. 3 plus 3 surrounding chlorine atoms, and the group number of chlorine is 7, so it comes to 24. So there should be 24 electrons totally in the molecule. So boron surrounded by 3 chlorine atoms. So you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. To find the lone electrons, group number of the central atom minus surrounding atoms into the valency of the surrounding atom. So 0, so there are no lone pairs. To find the hybridization, lone pairs plus the surrounding atoms, 3. 3 stands for sp2 hybridization. Same way, the formula can be applied to any molecule. To calculate for ions, if it's an anion, 1 should be added. If it's a cation, 1 should be subtracted from the number of electrons. So for nitrate, nitrogen belongs to group number 5. 5 plus 3 oxygen atoms, group number of oxygen is 6 plus 1, because it's an anion, you get 24. So when you write the structure of nitrate ion, nitrogen is a central atom surrounded by 3 oxygen atoms. So you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So 24 is achieved, but when you see nitrogen, it has got only 2, 4, 6. It should get the octet. So 1 electron is transferred here. So there will be a double bond in the structure of nitrate ion. To find the lone electrons, group number of the central atom minus 3 oxygen atoms which are surrounding, valency of oxygen. So 5 minus 6 plus 1, 0. There are no lone pairs. To find the hybridization, 0 plus surrounding atoms, 3. So 3 stands for sp2 hybridization. Same way you can try for other ions. For carbonate ion, 4 is the group number of carbon plus 3 oxygen, group number of oxygen is 6, and 2 because it's an anion with 2 negative charges. So when you write the structure of carbon, 2, 4, 6, 8, 10, 12, 14, 16, 18, 1 bond is 2 electrons, 20, 22, 24. It has got the 24. But when it comes to carbon, it has got only 6. So 1 oxygen will just put its electron in between, make it as a double bond. To find the lone electrons, group number of central atom minus surrounding atoms, valency of surrounding atom plus 2. So there are no lone electrons. So 0 plus 3 is hybridization, which is sp2. For sulfur dioxide, sulfur belongs to group number 6. 6 plus 2 into 6 is 18. So the structure will look like this. So 2, 4, 6, 8, 10, 12, 14, 16. So oxygen have been given 8 electrons each, but still the count has come to only 16. But there are 18 electrons, so there are 2 lone pairs on sulfur. So when you write this, for lone pairs, 6 minus group number of the central atom minus 2 into 2, valency of oxygen. So 2 electrons means 1 lone pair. Six minus 2, so for sulfur dioxide there is only 1 lone pair. Let us do sulfur dioxide again. Sulfur 6 plus 2 into 6, 18. So 18 electrons have been accommodated with 1 lone pair on sulfur. So the lone electrons will be 6 minus 2 into 2, that is 1 lone pair. So lone pair plus the surrounding atoms 3, it is sp2 hybridization for sulfur dioxide. Same way we can calculate for methane. Group number 4 minus 4 surrounding atoms 8. So 4 minus 4 is 0 for the lone electrons. Hybridization is 0 plus 4 hydrogen 4, that is sp3 hybridization. For CCl4 also same way, group number 4 plus 4 chlorine atoms. Group number of chlorine is 7, 32. So we get it like this. 4 group number minus 4 surrounding atoms into valency. So no lone electrons. Hybridization comes to 4. So sp3 hybridization. For BF4 minus, boron belongs to the third group. So 3 plus 4 fluorine atoms. Group number of fluorine is 7. Because it's an anion, add 1 here, you get 32. Remember, it should be an even number. So you have boron at the center with 4 fluoride ions surrounding. To find the lone pair of electrons, group number minus surrounding atoms into valency. Here once again, because it's an anion, you have to add 1. So there are no lone pairs. So hybridization is sp3. For ammonia, group number is 5 plus 3 hydrogen 8. So it's an octet, 8 electrons around nitrogen. For lone electrons, 5 is the central atom group number minus of 3 hydrogen. Valency of hydrogen is 1. So 2 electrons, there is 1 lone pair, which can be shown like this. There is 1 lone pair on nitrogen. To find the hybridization, lone pair, 2 electrons means 1 lone pair. So 1 plus surrounding atoms 3 in ammonia. So 4. sp3 hybridization. In water, oxygen is the central atom and there are 2 hydrogens surrounding that. So oxygen group number is 6, for plus 2 is 8. So you have oxygen flanked by 2 hydrogen atoms. To find the lone electrons, so when you write the structure, oxygen, there are 2 hydrogens on either sides. So hydrogen gets the doublet only, there is no octet for hydrogen. So here 2 plus 2, 4, 6, 8. There are 2 lone pairs on oxygen. To find the lone electrons, group number minus the number of atoms into valency of hydrogen is 1. So 6 minus 2 is 4. So there are 2 lone pairs. So hybridization is 2 lone pairs plus 2 atoms, which is 4, that is sp3 hybridization. For ICl, I will show you. You can ICl is 7 plus 7 is 14. Lone electrons is 7 minus 1, 6, that is 3 lone pairs. So 3 plus 1, 4 is sp3 hybridization. For PCl5, central atom phosphorus. So 5 plus 5 into 7. 7 is the group number of chlorine, so 40. Lone electrons is group number minus surrounding atoms into valency is 0. No lone pairs, so it is 5 sp3d. SF4, same way, 6 plus 4 into 7 is 34. When you write the structure, sulfur, so there are 4 fluorine atoms. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So there are 32 has come there, so there's 1 lone pair on sulfur. It should come to 34. So when you calculate lone pair, 6 minus 4 is 2. 2 electrons stands for 1 lone pair. So 1 plus 4 is 5. Hybridization is sp3d. Similarly, I3 minus. All the 3 are iodine atoms. So 1 iodine is at the center and the 2 remaining iodine atoms are on either sides. So here the number of electrons comes to 22. So to accommodate the 22 electrons, you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. 3 lone pairs on iodine. So the structure will be like this. Lone pairs will be group number minus number of surrounding atoms into valency plus 1 because it's an anion with 1 charge. So 6 electrons, that means there are 3 lone pairs. So hybridization is 3 plus 2, 5, sp3d. SF6, 6 plus 6 into 7, 48 electrons, no lone pairs. Hybridization number is 6, sp3d2. IF5, electrons 42. We do not know about the geometry now. The lone pair is 7 minus 5. It's 1 lone pair. Hybridization is 1 plus 5, 6, sp3d2. In IF7 also, we get the geometry as sp3d3. The hybridization number is 7. For XeF6 also, there are 50 electrons. So 1 lone pair, which means there is 1 lone pair on xenon. If you calculate, it will be correct. So the number is 7, sp3d3. So this magic numbers will decide the hybridization in the molecule. By a general rule, if the hybridization number is 2, it is sp, bond angle is 180, geometry is linear. sp2 is trigonal, sp3 tetrahedral, sp3d trigonal bipyramidal, sp3d2 is square bipyramidal or octahedral. Hybridization number 7 stands for sp3d3, which is pentagonal bipyramidal. These are the geometry of the molecules. But if you take the shape, the lone pair have to be taken into account. The presence of lone pair decides the shape of the molecule. According to valential electron pair repulsion theory, lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. What do we mean by that? This is a lone pair and this is a bonding pair. There will be repulsion between these two because all are, after all, electrons of like charges. These repulsion push the atoms and hence the bond angle will be reduced. In the case of ammonia, NH3, it is sp3 tetrahedral. The bond angle is supposed to be 109 degrees 28 minutes. But because of the repulsion between the lone pair and the bond pair on this side and on this side, it compresses the molecule and therefore the bond angle decreases to 107 degrees. In the case of water molecule, there are 2 lone pair bond pair repulsions and also there are 2 lone pairs. So lone pair repulsion being greater, they try to drift away from each other, compressing the molecule, and therefore the bond angle is 104 degrees. Though hybridization is sp3, geometry is tetrahedral, the shape is a bent shaped. So sp3 tetrahedral with 1 lone pair pyramidal, with 2 lone pairs bent, with 3 lone pairs it is linear. sp3d hybridization, 1 lone pair seesaw shaped, 2 lone pairs T-shaped and 3 lone pairs linear shaped. sp3d2, 1 lone pair square pyramidal, 2 lone pair square planar. So the lone pairs decide the shape of the molecule. By applying these formula and by knowing the number of lone pairs and the hybridization, the geometry of the molecule can be predicted. Hope this is helpful to you.